You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Structured generation refers to the practice of producing outputs in predictable formats, where information is arranged into schemas, lists, tables, or fields that can be read not only by humans, but also directly by machines. Unlike free-form text, which flows naturally but is often unorganized, structured generation ensures that answers are packaged in a consistent way. Imagine asking a human to take meeting notes. One person might write a full narrative, while another might bullet point decisions and action items. Structured generation enforces the second style, making sure that outputs always follow the same frame, no matter who or what produces them. This predictability is critical in modern AI, because it allows systems to slot outputs directly into downstream pipelines, such as databases or dashboards, without additional guesswork. Structured generation is therefore not just a formatting choice, but a design principle that bridges the gap between language models and real-world workflows. The importance of structured generation becomes clearer when you consider how AI systems interact with other applications. Outputs are rarely consumed as raw text alone. They are often fed into other tools that rely on specific formatting to function properly. For example, a compliance assistant might generate a risk summary that needs to be uploaded into an enterprise tracking system, or a customer support tool might need outputs organized into problem, steps taken, and resolution. Without structure, every output would require a human to clean and reformat before use, slowing processes and introducing errors. With structure, integration becomes seamless. Systems can read, process, and act on AI-generated content without additional layers of interpretation. Structured generation thus becomes a key enabler of automation, turning AI from a conversational partner into a functional component of digital ecosystems. Freeform text has its advantages, particularly in creativity and natural expression, but it struggles in contexts where predictability is necessary. Freeform outputs are like handwritten notes. They may be insightful, but they are inconsistent and difficult to scan at scale. Parsing them requires pattern matching, regular expressions, or manual review, all of which introduce friction. Structured generation, by contrast, is like filling out a standardized form. Each field has its place, and each entry can be read by both humans and machines without confusion. This contrast illustrates why structured generation is gaining traction. For casual conversation, free text suffices. For enterprise workflows, compliance processes, or technical systems, structured generation is indispensable because it eliminates ambiguity and reduces the cost of downstream processing. Schemas are at the core of structured generation. A schema is essentially a blueprint that defines the fields and organization of an output, such as name, date, summary, and recommendation. These schemas ensure that models know not only what content to generate, but also how to arrange it. Think of a schema as the table of contents for every answer. No matter the content inside, the structure is always the same, making it predictable and searchable. In practice, schemas can range from simple lists to complex hierarchical forms, depending on the use case. Enterprises often design schemas that mirror their internal reporting requirements, allowing AI outputs to plug directly into existing systems. By enforcing schemas, structured generation provides clarity, consistency, and alignment with organizational standards. JSON-like formats have become especially popular for structured generation because they are lightweight, flexible, and widely recognized across industries. JSON, short for JavaScript Object Notation, allows information to be expressed in key-value pairs that are easily parsed by machines while still readable to humans. When AI systems output JSON-like structures, developers can directly integrate them into APIs, applications, or databases without complex conversions. For example, an AI could generate a product description with fields for title, price, and features, each neatly nested inside a JSON object. This format is more accessible than full code or strict regex rules, making it a practical bridge between natural language and structured data. JSON-like outputs are therefore a cornerstone of structured generation, combining technical compatibility with human readability. The benefits of structured outputs extend well beyond technical convenience. By enforcing predictable formats, they improve reliability, automation, and downstream processing. A system that consistently produces the same structure allows organizations to design workflows with confidence, knowing that each piece of information will be where it is expected. This reduces the need for error correction and minimizes the risk of misinterpretation. For example, a financial institution using AI to produce compliance reports benefits when each output follows the same schema, making it easier to audit, review, and compare across time. Structured outputs also make collaboration smoother, since multiple teams can share and analyze AI-generated data without worrying about inconsistencies in format. Retrieval augmented generation (RAG) pairs naturally with structured outputs. When systems retrieve evidence before generating answers, structuring the output makes it easier to combine evidence with responses in a way that is both transparent and actionable. A RAG pipeline might return an answer that includes not only a text summary, but also a structured list of citations, confidence scores, and metadata fields. This ensures that outputs are not only accurate, but also packaged in a way that downstream systems can use for further validation or reporting. Structured generation in RAG workflows therefore strengthens both trust and usability, creating outputs that are grounded in evidence and organized for application. Constraints and prompts are the practical tools for enforcing structure. Models often need explicit instructions to produce outputs in the desired format, such as respond in JSON with fields for summary, key points, and citations. By embedding structure into the prompt, developers increase the likelihood that outputs follow the schema. Some systems use templates or reinforcement methods to push adherence even further. The challenge is that models sometimes deviate, particularly when asked to balance structure with natural language fluency. Prompting strategies thus play a critical role in structured generation, serving as the guideposts that steer models toward consistency. Enterprise applications provide some of the clearest examples of structured generation in action. In compliance, AI may generate checklists that track whether regulatory requirements have been met. In healthcare, structured summaries of patient notes may include symptoms, diagnosis, and recommended tests. In customer service, AI may populate metadata tables that classify tickets by urgency, category, and resolution status. These outputs are not just useful but necessary. Without structure, they could not be integrated into the formal systems enterprises rely on. Structured generation thus becomes the difference between AI being an assistant and AI being an operational partner. Challenges in enforcement remain a significant hurdle for structured generation. Models are prone to drift away from strict formats, especially when asked to balance structure with natural, human-like expression. A model may insert extra commentary, mislabel fields, or generate malformed outputs that break downstream systems. These errors are frustrating because they undermine the very reliability structured generation is meant to provide. Enforcement requires careful prompting, training, and post-processing to catch deviations. Developers must design systems that are forgiving of small errors but still maintain the integrity of the schema. This tension reflects the broader challenge of aligning generative models. They are built for flexibility, but enterprises demand consistency. Post-processing layers are often deployed to enforce structure even when models deviate. These layers validate, correct, or repair outputs, ensuring that they match the expected schema. For example, a system might automatically detect missing fields in a JSON object and insert placeholders, or it might catch malformed syntax and reformat it. Post-processing thus acts as a safety net, catching errors before outputs reach downstream systems. While effective, this adds complexity and cost to the pipeline. The ideal is for models to produce structured outputs consistently on their own. But until then, post-processing remains an important part of the solution. Structured outputs also make evaluation easier. When answers are consistent in format, evaluators can systematically measure correctness, completeness, and adherence to schema. Instead of manually parsing free-form text, systems can check whether fields are populated correctly, whether required elements are present, and whether values are in the expected ranges. This consistency transforms evaluation from subjective judgment into objective measurement. It also enables automation of evaluation, allowing systems to monitor performance at scale. In this way, structured generation not only improves usability, but also makes it easier to assess quality, supporting continuous improvement in AI workflows. Accessibility benefits are another important outcome of structured generation. By presenting information in consistent formats, systems make outputs easier to navigate, both for humans and for assistive technologies. Screen readers, for example, can process structured data more effectively than free-flowing text, improving usability for people with disabilities. Consistency also benefits multilingual environments, where structured fields can be filled in regardless of language, allowing parallel analysis across cultures and regions. Structured outputs thus contribute to inclusivity, ensuring that AI-generated information can be accessed, understood, and trusted by diverse audiences. Structured generation does, however, come with limitations. Rigid formats can reduce flexibility and creativity, making outputs feel mechanical. In contexts where nuance, style, or exploration matter, structured responses may underserve users. For example, a literary analysis written as a JSON object would be technically precise but emotionally flat. Structured generation also risks oversimplifying complex realities, forcing information into predefined boxes that may not fully capture nuance. The trade-off is between predictability and richness. Structured generation excels in environments where predictability matters most, but it is less suited for open-ended exploration. Recognizing these limits helps organizations deploy structured generation where it adds value and avoid it where it detracts from user experience. Finally, structured generation lays the foundation for tool use, connecting AI models with external systems that require strict inputs. Tools like databases, APIs, and spreadsheets expect information in specific formats. Structured generation ensures that outputs can flow directly into these tools without human mediation. This makes AI not just a generator of words, but an operator of systems, capable of triggering workflows, updating records, or populating forms. Structured generation is therefore the connective tissue between AI and automation, transforming natural language intelligence into actionable, machine-readable commands. Error handling is a critical consideration in structured generation because no matter how carefully prompts or schemas are defined, models will inevitably produce outputs that are incomplete or malformed. A missing field in a JSON-like object or a misaligned table column can break downstream applications, leading to errors that ripple across workflows. For example, if an AI-generated customer support ticket omits the priority field, the system responsible for assigning cases may fail to triage effectively, creating backlogs. Designing fallback strategies is therefore essential. These strategies may include default values for missing fields, automatic correction layers, or human-in-the-loop review for particularly sensitive use cases. Error handling in structured generation resembles error handling in software engineering. It anticipates failure and designs guardrails so that the system remains usable even when outputs are imperfect. Without such mechanisms, structured generation risks becoming brittle, undermining the very reliability it is meant to deliver. Schema validation is one of the most effective methods for catching and correcting these issues. Just as web developers validate HTML against predefined standards, structured generation systems validate outputs against defined templates before they are passed downstream. Validation ensures that each required field is present, values are in acceptable ranges, and formatting adheres to specifications. For example, a system generating financial reports might enforce that currency fields always contain standard codes like USD or EUR, never free text. By validating against schemas, organizations can block malformed outputs early, reducing the chance of errors cascading through other systems. This process adds a layer of discipline that transforms structured generation from best effort to guaranteed compliance. Schema validation is therefore a cornerstone of enterprise-grade deployments, where outputs must meet both technical and regulatory standards consistently. Adaptive structures attempt to balance rigidity with flexibility, allowing models to produce structured outputs that can accommodate variation. In practice, this means defining schemas with optional fields or flexible slots, rather than rigidly fixed templates. For example, a medical reporting schema might include mandatory fields like patient ID and diagnosis, but optional fields for secondary conditions or follow-up notes. Adaptive structures reduce the likelihood of model failure by providing space for nuance while still maintaining overall organization. They recognize that real-world data is messy, and forcing every case into identical boxes may strip away valuable information. Adaptive structures thus act like expandable filing systems. They ensure consistency where it matters most, but leave room for complexity where it is unavoidable. Designing adaptive schemas is a growing area of research, as organizations seek to capture the richness of human knowledge without sacrificing the predictability machines require. Integration with APIs is one of the most powerful uses of structured generation. APIs, or application programming interfaces, expect inputs in predefined formats, and free-form text cannot reliably meet those expectations. Structured generation solves this by producing outputs that match API requirements exactly, enabling seamless machine-to-machine communication. For instance, an AI assistant might generate a structured command to schedule a meeting, outputting fields for date, time, and participants in a JSON object that can be passed directly to a calendar API. This bypasses the need for manual translation or error-prone parsing. In effect, structured generation turns natural language into executable actions, linking conversational interfaces with backend systems. This capability is what enables AI-powered agents to operate not just as advisors but as actors, capable of directly interacting with digital environments through structured, reliable outputs. In search systems, structured outputs have already proven invaluable. When a retrieval-augmented model answers a query, structured generation allows it to package the response, along with supporting citations, confidence scores, and metadata fields. For example, a query about climate change policies might return a structured output containing summary, sources, policy year, and jurisdiction. This organization ensures that evidence is visible, metadata is preserved, and downstream applications can filter or sort results efficiently. Structured outputs also allow multiple answers to be grouped consistently, supporting tasks like ranking or comparison. By standardizing responses, structured generation makes retrieval systems not just smarter but more usable, ensuring that information can be trusted, cross-checked, and integrated into decision-making. Without structure, answers risk remaining black box statements. With structure, they become transparent, actionable, and auditable. Agents, or AI systems that combine multiple tools, rely heavily on structured generation to coordinate decision-making. An agent deciding whether to call a search API, a calculator, or a database cannot function with ambiguous free-form text. Instead, it requires structured outputs that specify the tool to be invoked, the parameters to be passed, and the expected return format. For instance, a multi-tool agent answering a financial question might generate a structured plan. Step 1. Retrieve stock data. Step 2. Calculate average. Step 3. Format into chart. Each step is encoded in a predictable schema that the agent can follow. Structured generation thus serves as the planning language of AI agents, ensuring that complex workflows can be executed reliably. It transforms AI from a generator of prose into a conductor of processes, orchestrating multiple components through the discipline of structured outputs. Evaluation benchmarks for structured generation focus less on the content of outputs and more on their adherence to schema. While traditional evaluation measures relevance or correctness, structured generation is judged by how consistently models obey formatting rules. Schema adherence rates, for example, measure the percentage of outputs that pass validation without correction. Other benchmarks test whether models fill all required fields, avoid hallucinating extra fields, and handle optional fields gracefully. These measures may seem technical, but they directly impact usability. A system that produces brilliant content but fails to match schema 20% of the time creates more work than it saves. Evaluation ensures that structured generation delivers not just intelligence but reliability. Benchmarks thus play a crucial role in pushing the field toward outputs that meet the needs of both humans and machines simultaneously. User trust is enhanced significantly when outputs are presented in predictable formats. People value transparency and consistency, and structured generation delivers both. For example, if every answer to a compliance question is presented as a table with requirement, status, and evidence, users quickly learn how to interpret results without rethinking the layout each time. This predictability builds confidence. Users know where to look and what to expect. By contrast, free-form outputs force users to parse varied wording and formats, which can erode trust over time. Structured generation therefore functions as a design tool for shaping user perception, signaling professionalism, reliability, and care. When combined with citations or provenance, structured formats create an experience that feels less like guessing and more like consulting a trusted reference. Structured generation also extends into multimodal outputs, where information spans text, images, and even audio. For example, an educational AI might generate a structured package that includes a written summary, a relevant image, and a short audio explanation. Each component is slotted into predefined fields: text in one slot, image in another, audio in a third, making it easy to present consistently across platforms. This approach is especially important in accessibility contexts, where structured outputs ensure that information can be consumed in multiple modalities. For instance, text summaries can be read by screen readers, while images carry alt text descriptions in structured fields. Multimodal structured generation highlights how schemas are not limited to text, but can serve as universal containers for diverse forms of knowledge, creating richer, more inclusive user experiences. Cost efficiency is another often overlooked benefit of structured generation. When outputs are predictable, organizations spend less time and money on error correction, manual validation, or integration fixes. Consider a customer service platform where structured generation produces consistent ticket summaries. Instead of requiring human staff to reformat or interpret messy text, tickets flow directly into the resolution pipeline. This reduces labor costs and accelerates processing times. Structured generation also lowers compute costs by minimizing retries and corrections. When outputs adhere to schema from the start, fewer cycles are wasted. Over large-scale deployments, these savings compound, turning structured generation into not just a technical improvement but a financial advantage. Predictability saves money, a fact that makes structured generation attractive for enterprises under pressure to optimize resources. Domain-specific applications of structured generation highlight its versatility. In healthcare, structured patient summaries can include fields for symptoms, diagnosis, and treatment plan, ensuring doctors can scan and verify quickly. In finance, structured outputs can produce balance sheets, risk assessments, or audit trails in standardized formats. In law, case summaries can be generated with precedent, jurisdiction, and decision fields, aiding legal research. Each domain benefits from schemas that align with professional standards, ensuring that AI outputs integrate seamlessly with established workflows. These examples underscore that structured generation is not abstract theory but a practical necessity in high-stakes industries. By embedding domain expertise into schemas, organizations transform AI from a general-purpose tool into a specialized partner tailored to their needs. Research directions in structured generation focus on making models better at obeying constraints. Grammar-based decoding, for example, enforces adherence to formal rules during text generation, ensuring outputs always match schema. Constraint-based decoding uses mathematical methods to steer outputs into predefined formats, even when models stray. These innovations reduce the need for post-processing, and increase confidence in raw outputs. Researchers are also exploring adaptive schema enforcement, where models dynamically adjust formats based on user intent while still maintaining structure. These methods represent the next frontier of structured generation, pushing it from often reliable to nearly guaranteed. They reflect recognition that structure is not a cosmetic feature, but a core requirement for enterprise-grade AI. Security considerations are increasingly important in structured generation, especially as AI is integrated into workflows with sensitive or high-risk data. Enforcing strict formats helps prevent injection attacks, where malicious input attempts to trick systems into unintended behavior. For example, if a model is expected to produce only JSON fields, strict enforcement ensures it cannot slip in executable code or untrusted commands. Structured outputs also make it easier to audit for compliance, since every field is predictable and scannable. This predictability reduces the attack surface of AI systems, making them safer for deployment in enterprise and government contexts. Structured generation thus doubles as a security feature, not just a usability feature, aligning reliability with protection. Looking to the future, structured generation is poised to become standard practice in enterprise AI systems. As organizations demand more integration with existing workflows, free-form outputs will no longer suffice. Structured formats will be expected by default, much like data validation is expected in modern software. Over time, we may see industry-wide standards emerge for schemas in healthcare, finance, law, and other sectors, enabling interoperability across systems. Structured generation will likely pair with grounding and provenance, creating outputs that are not only predictable but also verifiable and auditable. This trajectory reflects the broader shift in AI from novelty to infrastructure. As infrastructure, AI must be predictable, reliable, and safe, and structured generation is one of the pillars that makes that possible. Finally, structured generation provides the bridge to tool use, the subject of the next episode. By producing outputs in strict formats, AI systems can interact with external tools, databases, and applications reliably. For example, a model generating structured commands can trigger a calculator, query a database, or populate a spreadsheet. Without structure, these interactions would be fragile. With structure, they become robust. Tool use represents the next step in making AI not just a conversational partner, but an operational collaborator. Structured generation lays the groundwork by ensuring that AI outputs are ready for execution, not just for reading. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.